I have with me, next to me, a systems engineer on the InSight mission from Jet Propulsion Laboratory, Farah Alibay.
Hi.
Hi, Farah. So nice to have you here joining us.
Yeah, thanks for having me.
And then also Patrick So, some of you will recognize also from All Space Considered, who has been covering the InSight mission for our show. So
Hello.
we're here with Farah. And Farah, tell us a little bit about how you became a systems engineer on the spacecraft and started working at Jet Propulsion Lab.
Yeah, I feel like maybe like every kid, I wanted to be an astronaut when I was growing up. I know that you had Buzz Aldrin here earlier, but what changed my life was Apollo 13 and seeing that movie. So I have a lot of friends in the industry here, and I always tell them, Hollywood did play a part in my life because that's how I discovered space. Eventually discovered that, being an astronaut wasn't exactly a viable job. A lot of people apply and not many people get it. So my backup was, I actually realized that what I enjoyed about space was the teamwork that happens between the teams, and we all work on things that are essentially impossible. No one's ever done them before, and it's challenging, and that's what I really enjoy. And so I ended up pursuing a degree in aerospace engineering. Did my PhD at MIT, and during that time I interned at JPL. JPL actually takes on, our population every summer grows by 10%. So we currently have 600 interns ranging from high school all the way to graduate students that come to JPL, discover what we call our universe. That's how I got my foot in the door, and that's how a lot of younger engineers actually have gotten their foot in the door. And when I joined JPL about 5 years ago is when I started getting involved with the InSight mission and its partner mission, Marco.
Wonderful. And what does that mean, systems engineer?
So what I tell people is that I'm a jack of all trades and master of none, because really my job is to make sure that everyone on the team gets along. So it's 75% technical and 25% leadership and people skill. Essentially what happens when you build a spacecraft is you're limited in terms of the amount of resources you have, right? You have a rocket that has a maximum amount of weight that you can launch to Mars, for example, and then you have different subsystems that are competing against each other for resources. So the power person maybe wants the biggest arrays they can have, the thermal person wants to stay as warm as they can, the instruments absolutely want all the data, and then, the telecom person tells you, well, I can't really get you that much data all the way from Mars if you're only giving me this tiny antenna. So you somehow have to,
They all go into Thunderdome and work it out.
Yeah, that's what it is, right? So I have to talk to each of them and figure out, well, what is it that you actually need? Because we only have this much money, and I can't give it all to you because otherwise we won't be doing any interesting science. So it always comes down to trading some of these resources so that we can get as much science done as possible with the amount of money that we have, essentially.
And so as the engineer, you just try to work on different scenarios and how those trades all play out?
Exactly. So usually an early mission concept, that's what systems engineers do. They sort of figure out, okay, what is it that the mission has to do and what are the trades? On InSight, I was actually a payload systems engineer. So my job was to make sure that when the instruments were delivered, so actually we have, and we'll talk a little bit about the mission, but we have some foreign contributions. And my job was actually to make sure that once the instruments were delivered, they were integrated and tested properly. So we actually put the lander and the instruments through all the rigors of what it will see. Like we call it a shake and bake. So we shake it, and that's the same shaking as they'll feel as we land on Mars, and that's actually the worst shaking environment. And then the bake is essentially where we take it to hot and cold to mimic the heat and coldness of space that we're seeing. So that's one of the types of tests that we do, where we put the instruments through those environments, so that by the time they get on Mars, whatever happens to them, they've seen worse, and we know they're going to work.
So it's worse to go land on Mars than it is to launch, huh?
Yeah, as it
That's
turns
very
out.
surprising.
I was pretty surprised about that, because I didn't know that was a driving scenario. Yeah, because you think like, oh, right, like a rocket is just essentially a barely controlled bomb, right? And you're on this thing and it shakes a lot, but apparently landing is a lot worse because of just hitting the atmosphere and shaking around as you do that.
That's amazing.
So, yeah.
Well, you brought with you some slides, and if we can go to those slides, we've got a little intro here. There you are, Farah Alibay, Insight Payload Systems Engineer. Do you say that to people at parties and they say, what do? You say, I'm a payload systems engineer, and then what do they do?
I just say I'm a rocket scientist.
Oh,
it's much better.
Good answer. That is much better. So you're on this mission Insight. Can you tell us a little bit about that, and what is Insight supposed to do for us?
Yeah, so maybe if we go to the next slide, I have a pretty picture, I guess. So one of the interesting things, right, and we're here in California, so you know about earthquakes, right? But one of the things that I maybe didn't realize before I even joined this mission is that the way that we know about the interior of the Earth and what it's made of, or what it's composed of, is because of earthquakes. Because of the waves that are triggered whenever we have an earthquake, the way they reflect and refract is what tells you about the interior of the Earth. So we know, for example, fun party fact that I've never used at a party, but my PI has told me this, is the crust of the Earth is actually, the ratio of the crust with the rest of the Earth is about this thickness, the same thickness as a tomato skin. So that's about as thick as it is on a normal big tomato. That's the ratio.
You definitely have to use that at a party.
Yeah, I don't know who that works with though. But then we also know, right, that there's a liquid core and a solid core, and the liquid core is the reason why we have a magnetosphere, right? That's why we have a magnetic field, because this liquid metal core is moving, creating a magnetic field. The magnetic field is actually the reason why there's life on Earth, right? Because the sun is constantly bombarding us with energetic particles, and that magnetic field is catching those particles and protecting us, and also protecting the atmosphere from being blown away from that solar wind. Now, on the other end of the spectrum, we have the moon, right? And the moon, actually, we flew a seismometer to the moon. As it turns out, the moon is boring. It's so dead. There is nothing going on. It is just a solid piece of rock with some differentiation, but nothing moving.
And is that what we're seeing here in this slide?
Yeah, that's on the far right on the slide. So Mars is somewhere in between. Mars is a rocky planet, so it formed probably like Earth, right? But it evolved differently. For example, we know that Mars used to have a magnetic field, but it went away at some point. There's evidence on Mars there's actually remnant magnetic fields, but it no longer has a global magnetic field. So does that mean that maybe it had a liquid core and it's gone? We know it used to have an atmosphere and it's no longer there. So Mars somehow formed the same way as Earth, but evolved differently. And that's what we're trying to figure out. And so, we often joke on Insight that, we could have done this science on really any rocky planet, right? Venus is also very different. We're just interested in the evolution of rocky planets. So why are we going to Mars? Well, the reason why is because it's actually the easiest planet to go to. It's still really hard, but somehow we decided that was the easiest place to go to do these investigations.
So between these three objects, Earth, if they were like bells, the seismic waves for the Earth would be a dull thud. For the moon, it would ring like a bell because it's solid all the way through.
Yeah.
And then Mars we're trying to figure that out.
Yeah, that's a really good analogy.
Yeah.
I like that a lot. Yeah, we actually don't know at all what it.
So we'll find out when Insight lands. If Mars thuds, then we'll know there's a
liquid center, maybe.
Yeah,
perhaps.
And if it rings like a bell, that's a lovely thought.
That's like the moon.
We've had we have at Griffith Observatory a seismograph.
Oh.
And there's one that kids can go jump by, and I know you guys have something similar for Insight, and watch the little needle go back and forth. But we have a real one that measures earthquakes, and after some of the really big ones, you'll see the ringing. It just continues in these, very regular waves. It's kind of a stunning thing to see that the whole Earth is ringing in the aftermath of an earthquake.
Yes, that's what we're hoping to see on Mars. But
That's
Mars
amazing.
is different from Earth, right? There's no tectonic plates. And yet it has the biggest volcano in the solar system. I mean, it doesn't flow anymore, but and it has, a canyon that's 3 times deeper than the Grand Canyon.
What's up with that planet?
Yeah, we don't know. That's what we're trying to find out.
So those are the science goals of the mission.
Yeah, essentially. So we're doing that. We're studying the interior of Mars, and we're using really 3 experiments, and we have 3 instruments. We're doing it through seismology, so we have a seismometer, and that's what we've talked about. And then there's 2 other things. We're doing tracking using the antennas on the lander. We can actually track the position of the lander to within 10 meters. So Yeah, and since we know where we landed and we know where Mars was, any change in the position that we're seeing is actually just the planet flexing and wobbling and or nutating, right?
Oh,
so
that's
it's
so
like
weird.
wobbling around its axis. It's
Yeah.
like if you've ever been at home and taken, I don't know if you've ever done this, if you haven't, go home and do it, I guess. Take a boiled egg and a raw egg and spin them. And you'll tell that they spin differently because of the content on the inside, right? I feel like I did that as a kid.
Yeah.
Much to my mom.
Oh, that's how you can find out in the fridge if they've got hard-boiled eggs or
centered
not.
or-
Oh yeah, that's
Or solid
okay.
No, yeah,
Yeah.
because if you don't mark them, then and so you can do this. It's a very useful trick.
Yeah.
You just spin it, and then you stop it for a second and take your hand away. And if it continues to spin, there's liquid on the inside because the
Because it's
liquid is
still
still
moving,
going.
yeah.
But if you stop it and then take your hand away and it just sits there, it's solid all the way through.
Yeah, the spinning pattern is also different for the two.
All the things you learn by watching this webcast.
So that's exactly what we were doing on Mars, is seeing how Mars is spinning, and that gives us an idea of whether it's liquid or solid on the inside. And then we also have a heat flow probe that's actually going to go down the surface of Mars 5 meters, that's about 16 feet, and it actually has a thermal sensor on the end, so basically something that measures temperature. So as we go down, it's going to study that heat signature. And then when you get down below 10 feet, what happens is that you're no longer seeing any change in temperature that you're seeing. You're now isolated once you get below 10 feet from any change day or night or summer or winter that might be happening on the surface. You're far down enough that any temperature change that you're seeing is actually from the core or any heat emitting elements below the surface.
And do you expect the temperature to go up when you're...
Well, we don't really know. There's two experiments we're doing. We're actually looking at, there's also a little heater at the end of the probe. And so we're actually going to send pulses of heat as we go down. And that gives us an idea because we have a tether that we drag along with it. Actually, if we go to the next slide, you'll see the heat flow probe. So there's a probe with a tether. You can see that HP3 instrument.
I see over here. Let me get the little arrow.
Yeah.
This.
So
That's the tether.
Yeah, that tether has little temperature sensors on it, so it can measure temperature. So when we send these heat pulses, the way that the heat diffuses up can give you an idea of what the soil is made of. And then below the surface, we're actually just interested in seeing what happens if there is a difference. So there's a long-term monitoring that we want to see. Oh, is the core still cooling? Is it still emitting heat? Is there other properties that are, other elements below that are emitting heat? We don't know. That's part of the magic of
That
science.
is
missions,
really
right?
exciting. When will we start to get an answer?
So we launched on the 5th of May out of Vandenberg. That was the first interplanetary launch out of Vandenberg, which was pretty cool.
I remember. Yes, that was.
We're currently about 15 million miles away from Earth and 21 million miles away from Mars. So we hit the halfway point sometime next month, and we'll land on Mars at midday Pacific time on Cyber Monday, so the Monday after Thanksgiving. So while you're doing your shopping.
So what time did you say it would be?
It'll be around noon on
noon Pacific time.
Yes, noon Pacific time.
Okay,
About
so if
2
you
p.m.
everybody's going to be at their computer doing their shopping.
Yeah.
So
just
you'll be
like
at your
watch it in the
computer.
corner,
Just go turn on the JPL feed.
Yeah, it'll be on NASA
That's a
TV for sure,
no-brainer.
and you'll be able to see what happens. So
tell us about this entry and well, let's go back to the mission overview. As you said, we can go to the slide. It's on its way there. And then, so you've got approach, and then something called EDL and surface op. So we're in cruise right now.
We like acronyms at JPL. Or at NASA, JPL being an acronym of itself. So we're in cruise right now. The approach phase is when we start getting closer to Mars. About a month away is when it starts getting busy for us. That's when we start really correcting the trajectory and getting ready for entry. And then the scariest part of landing on Mars is going to Mars is the actual landing, and that's what we call entry, descent, and landing. So if we go to the next slide, there's actually a little animation, and we can start it. If you, there we go. So as we approach Mars, what will happen is we first get rid of the cruise stage. That's the solar arrays that we were carrying during cruise to power the spacecraft. Then we enter the atmosphere, and the atmosphere is actually fairly thin, but it's thick enough that it's actually kind of annoying and you have to account for it. And at this point, the heat shield is what's burning up. It's actually made out of cork, is something that I found out.
Wow.
About 5 miles from the surface, we deploy a parachute, a supersonic parachute, and that's going to slow us down down to about 1 mile above the surface. So then we get rid of the back shell, and that's actually InSight's legs that actually pop out from the bottom. And then about 1 mile from the surface, we then fire little retro rockets on the lander. So it has its own little rockets and slows itself down. So unlike other spacecraft like Curiosity that had the sky crane, this has its own little thrusters, and it just touches down on the surface all by itself.
So how long does it take from orbit to landing? Is it like 6 minutes of terror?
Yeah, it's around the 7-minute mark from hitting the atmosphere to landing on the surface, and it's all automated. The light time delay is about 7 or 8 minutes as it is. So by the time we get there, so we plan everything ahead of time, and then we sit back and watch as the data comes down.
And are you engaged will you be in that room that everyone watches when...
So I will be watching. I won't be working that day because my job is actually to work on the instruments. So I actually work on the deployment phase when we get these instruments from the deck down to the surface. And actually, if you skip a couple of slides, maybe, I think...
Okay, let's see here.
I think there's actually, there's a video right here.
This one?
Yeah, of what happens once we get on the surface. So when we get on the surface, the instruments are actually on the deck of the lander. So what we do is we have a robotic arm and we take the instruments from the deck and we'll place them on the surface. That seems easy, but if you've ever played that claw game at the arcade, that's basically that, but all the way on Mars with light time delay. So,
7 minutes of delay.
Yeah, so we can't do it in real time. We somehow have to send, we have these little robotic arm with a little claw that grabs a super sensitive seismometer and pulls it off and gets it from the deck to the surface. So I often joke with my friends who, have friends who are on the navigation team and worry about EDL, and I'm like, I'm not worried about landing on Mars. We've done that before, but grabbing an instrument in that last meter, putting it on the surface, and then we have to put a cover on it. And that's a wind and thermal shield so that the seismometer that's really sensitive can actually detect seismic activity rather than wind activity and things like that.
There are some context cameras on the lander there. Will we see pictures right after landing, or how soon will we see them?
So there's a camera on the deck, and then there's a camera on the arm. So one of the first pictures we'll actually take is a picture from the deck. I'm not quite sure exactly when it will be released. It just depends on how fast we can get it down from the orbiters, but likely within the first week or so we'll start seeing those pictures. And then one of the coolest pictures we'll take is when we release the arm. We'll actually take that camera and turn the arm around and take a selfie, because most of the people on the mission are millennials, but also because we want to make sure that actually the instruments, at least that's what we tell our lead engineer, right? We want to make sure that all the instruments are on the deck. So that'll be a pretty neat picture that'll come out too.
That's nice.
And in fact, there are pictures that are coming through EDL, are there not? From
not during EDL. There won't be any pictures during that time, but we will get data before and after. So you might be able to get, the orbiters will be pointed towards that site, so we might be able to get a high-level view of what the ground looks like after landing.
Oh, okay.
But again, those are all opportunistic, so we'll have to see how the lineup works out. EDL is actually one of the scariest times, so we try to do as little as possible other than the bare essential. But one of the missions I did mention is called Marco.
Yeah.
And Marco's job is actually to help us out a little bit during EDL.
That's right. So, if we can go to the slide.
Yeah, so Marco is a pair of shoebox-sized spacecraft. It's actually the first mission I worked on at JPL. The idea for this mission, which is basically two engineers and a paper napkin idea, came around when I first started at JPL. So it was literally that week, these engineers were thinking like, how can we get the UHF signal, this radio signal that's coming out of InSight, down to the Earth a little bit faster? And to give you an idea of why this issue is happening is, as InSight lands on the surface, right, it's going to be sending data through its antenna that talks to the Martian orbiters. And it'll actually be talking to an orbiter called the Mars Reconnaissance Orbiter, MRO. The issue is MRO will be digesting all that data, but it can't send it back in real time. And as it passes over InSight, it actually sets behind Mars with respect to Earth. So as we view Mars, like if you were seeing it from here, for example, you'd have a direct line of sight with MRO, but right after landing, it would pass over the pole and over the other side. So then there's no way to talk back until it rises again at the bottom, right? So that's about 4 or 5 hours. It's not a big deal, but when your baby is landing on Mars, the last thing you want to do is wait 5 hours to hear, to wait and hear what happened.
Yeah.
And so that's why we designed these CubeSats that are making their own way to Mars. They have their own little propulsion system, and they're just going to sneak in and listen for that signal as InSight is landing and transmit it back in near real time. Obviously, there's still light time delay. We can't go faster than light, but we will get the signal, about 7 or 8 minutes after InSight has actually landed, and of everything that's happening.
That's a lot
No.
better than
Yeah.
5 hours.
Yeah.
Now there are two of them.
Yeah.
Is there a reason for two?
Yeah, this is the first time we were doing this, and so we figured that if we flew two, we would have a better chance of at least one making it.
Oh,
Both
as a
of them are
backup.
still fine. As it turns out, we did an okay job. They are single string is what we call it, meaning that if something goes wrong with any of the switches or anything, then we would lose the whole spacecraft. So normally we would build things what we call dual string, where there's always a backup. So in this case, the backup is the other spacecraft.
And-
If both make it, we might change just the orbits a little bit so we get different levels of coverage at different times. But
Well, for our last image here, if we can go to the computer, I want to show this picture, which was taken, I believe.
This was taken
Yes.
just
Yeah.
few days after launch, and that
And
blew
what
up
are we
there.
looking here? Yeah.
What is it?
Okay, well, we have a little annotation.
that's Earth and the Moon right there.
Yeah.
So Marco has two cameras, one on its deck and one below. And we use this camera to look back, actually to make sure that the antennas have been deployed properly, but also to look back. And the inspiration was the pale blue dot. So we were able to capture Earth and the Moon on our way out.
Was that an exciting time to see this picture coming through?
Yeah, well, that was also the first picture we got out of it, but it's
Yeah.
pretty incredible how pointed it is, and
know.
and it's
Beautiful.
And it's funny because I remember testing that camera in the lab, and I used my face as the target. I even have a picture of my face with that camera, and now I'm like, oh, look
You,
at that.
the Earth, it's, takes
Yeah, it's
pictures of
about the
whatever it's in
same.
front of it. But it's actually, if it can actually go back to that for just a second, I just want to make the comment, and although this may seem obvious, I think I'm just compelled to say that the moon is round, Mars is round, and Earth is also round. It is not flat. We have pictures from spacecraft out there, and people like Buzz have been to the moon and seen it,
Yeah.
seen Earth, and so I just thought I would take this opportunity to have a little public service announcement.
It's also incredible how small it is when you look back. It's not that far, right?
Right.
And it's our only
Right,
planet.
I know.
So now, what will happen after EDL? Do these spacecraft sail back past Mars, or they
Yeah,
go in
so we
orbit?
don't have actually enough propellant to get into orbit because our sole mission was to do the entry, descent, landing, telecommunication relay. So they're essentially what we call in the heliocentric orbit. So they're in orbit around the sun, and they're going to stay that way forever. So really after, if they make it to Mars, after that we'll be studying how the systems behave, right? These are off-the-shelf components. It was built in 18 months. It's a really fast build. And so what we want to understand is how do these systems compare to the really expensive spacecraft that we build? And because the real goal is this is a technology demonstration mission. So the idea is in the future, if we go to a planet where maybe we're not so lucky and there's no Aurora or Odyssey in orbit, we can use things like Marco to do telecommunication relay and help us out.
So you actually do a orbital insertion and maybe.
Possibly, or we could do flybys. So the idea is we really want to see how the systems behave to, from there, evaluate what we can do in the future. Right?
Well, it is so lovely to meet you, Farah, and what an exciting time for you. What an
Yeah.
exciting career you're building. That's really very
That's
cool.
exciting, yeah.
And we're so happy that you were able to join us tonight on this beautiful night. Look up there and know that your little spacecraft, your baby, as
I
you heard
know,
it,
that's so
is winging,
exciting.
well, not with wings, but floating, cruising its way.
4 months will be there.
4
so,
months. Yep.
Yeah.
So again, thank you so much for coming and
You're
joining us.
welcome.
And everybody, I think you're going to want to be on your computer on the Monday morning after Thanksgiving, and tune into the Jet Propulsion Labs feed, because you're going to want to see this thing land.
While you're shopping.
So, yeah, while you're shopping. Yeah, you can put the shopping aside for just a few minutes while we do something like land on Mars.
You can follow at NASA JPL and at NASA Insight, and leading up to on Facebook and Instagram, and leading up to the landing, we'll be updating everyone on exactly what time and how the spacecraft's doing, and that's where you'll also see the first pictures of Mars from Insight. Just so exciting.
Wonderful.